All right. Sorry. My name is Kostya Kortchinsky, and I will be talking about Cloudburst, which is an exploit that would allow a user to escape a VMware guest and run code into the host. Cloudburst is a name that David Toll came up with. It's like he likes to give code name to stuff, which is the reason for that. I'm currently a senior security researcher for Immunity Inc., which is based in Miami Beach, Florida. And yeah, Immunity Inc. Has several products: Immunity Burger, Canvas, Silica, and that's if you have heard of the company. And yeah, I'm French, not Russian. And that's in order to avoid the awkward conversation at the end of the talk when people start talking to me in Russian, and I totally don't know what's going on. Okay, about VMware and the VMware security, we found a cool quote in the next wave. There is the NSA newspaper-ish type of stuff, and they were talking about their NetTop stuff, which is like some kind of appliance that would allow classified and unclassified data to be running on the same hardware using a virtualization stuff, VMware, in order to have a VM that is unclassified and a VM that is classified. And they said, I'm reading that there, using 7 analysts over a 10-week period and with some limited input from VMware developers, we explored the ability of the core NetTop technologies, VMware running on a Linux host, to maintain isolation. The results of this first study were encouraging. No apparent stopping flows were identified. So that's their stuff. Obviously, they spent a reduced amount of time. But what I'm going to try and prove with this presentation and this exploit is that everything that is probably based on the virtualization technology in order to increase the security or the separation between classified and classified is as secure as the product that is ensuring the virtualization stuff. And there is a bunch of misconception about guest to host escape. There has been a bunch of vulnerabilities that have been published in the past. Here is a list of some CVE. The few good ones were the one that were unfortunately not default, but used the shared folders functionality of the VMware tools and of VMware in order to be able to do a directory traversal stuff and access some files on the file system. So that's Greg McManus is credited for that, as well as Core, who expanded the vulnerability to the shared to Unicode. One of the cool stuff also was Raffles' work, and he found a bunch of interesting vulnerabilities that would allow somebody to get out of the guest and execute stuff on the host potentially. One was in 2007, a heap overflow that was dealing with some I/O related to the video device. So this is some stories, and yet in nowadays you still see in presentation people who are advising the use of a virtualization software in order to improve the security. So this slide is taken from a SourceFire person, a presentation, and he was doing a presentation about the security of PDF. And obviously, as we all know, Adobe and PDF is not like as secure as we want it to be. And he's saying that if you want some more information, he can send you a PDF, but you should open it in a VM. I think I'm not saying that it's a bad thing. I'm saying that thinking that because you're opening a PDF inside a virtual machine will not prevent a skillful attacker to, first of all, exploit a vulnerability in your PDF reader, then exploit a vulnerability to increase the privileges if you're not admin, and then exploit the vulnerability that will break out of the guest OS and execute code on the host. Obviously, it takes a lot more skill than the regular PDF open and get owned, but it's not something that is impossible, and hopefully, if the demo works out at the end, we'll see exactly what happens. The first part of the presentation, I will try and go through the steps of the audit that was carried against VMware and what I did in order to find the flow, and then I will go into the details of the vulnerability. Basically, starting with a very general approach, and then going into the details of all the small stuff, and then to the exploitation process. Here is an image taken from the VMware documentation that represents the, well, pretty much what everybody, I guess, knows about virtualization, that you have a layer of hardware, then the virtualization layer, and then you have some virtualized devices on which you can run, well, whichever OS you want, basically. The important part here, and the stuff that, that is written at the bottom of the slide, is that every device is emulated on the host, meaning that the guest can access those devices. Obviously, if he wants to display something on the screen, if he wants to do some network traffic, he will have to have access to the network card. The code that is responsible for the emulation of those devices is running on the host with the privileges of whichever process is running on the host. So on Windows, those devices are located inside the VMware-vmx.exe binary. Under Linux, it's VMware-vmx. The advantage of the Linux part is that VMware-vmx is security root, meaning that if something happens, you end up with root privileges under Linux. So why devices? First of all, I don't have enough knowledge about virtualization and everything that is lower layer, probably like Raphael or Joanna have. So I'm stuck with auditing code that is Ring 3-ish, and that is written usually in C, C++, and that does not require low-level knowledge of what's going on in the CPU and stuff. I'm just like reading assembly, guessing if there is something wrong, and then writing the exploit for that. The interesting part of the devices is also that they are common to all VMware products, meaning that they have the same code that will emulate the same device on any of the VMware product. Meaning that if you're auditing VMware Workstation under Windows and you find a vulnerability in one of those devices, then the code will be shared with ESX server, will be shared with Fusion, obviously shared with Player because it's pretty much Workstation stripped down. And yeah, if the vulnerability is there, it will be there in every single product. And you don't have to rely on the fact that your CPU is an Intel CPU or AMD CPU or whatever you're running. Once again, they run in the host process. They can be accessed from the guest, obviously, either through port I/O or through memory mapped I/O. They're written in C and C++ most of the time, which is cool because C and C++ are not, well, are still open to some vulnerabilities most of the time. And they have the advantage to sometimes parse some complex data, meaning that something is sent from the guest, they have to parse that, then they have to render whatever was sent or to reply to that. And well, usually if there's some parsing, there might be some bugs, and it turns out there was some bugs. Here is a list of the devices in a virtual machine. This screenshot is from XP SP3 running on an ESX server. I wrote down, there's a bunch of devices, a bunch of virtualized devices. I only wrote the one on the slide that have either some port I/O available or some shared memory available. So the first one that is bolded out is the video adapter. Why? Because it's most likely the one that will have to parse the most complex data and do the most annoying things. Plus, it has a huge amount of shared memory, and we'll see exactly why. But it looked like a pretty good guess to start an audit of a VMware binary. Then there is a floppy controller, IDE controller, keyboard controller, and everything. The one that have been stricken at the bottom, the USB controller and the audio adapter, are only available on Workstation. There is no USB or audio on ESX, meaning that if you want to have something that will also target ESX, which was the point, you probably don't want to look at those. Otherwise, you're stuck with Workstation. What is Cloudburst? Cloudburst is really the combination of 3-4 vulnerabilities that were discovered in VMware, Workstation, ESX, and whatever. Those vulnerabilities all combined together make the exploitation possible on most of the platform. The first one would be a host memory leak, meaning that from the guest you can read any memory in the host process. Obviously, it's not like the whole memory of the system. It's only the memory of the VMware-VMX binary that is currently running. But it's good enough because if you want to do some fingerprinting, if you want to know where you are, if you want to get some addresses, which is usually useful to disable DEP or go around some protections like that, it's pretty cool. The other ones were arbitrary memory write from the guest into the host, meaning that when you're in the guest, you can write whatever you want, wherever you want in the host process memory. There is one relative, meaning that you have to know the base address in order to write minus or plus relatively to that address. And there is an absolute one, meaning you can say, I want to write something at 800000, and you write that stuff. The fourth one, which is not really a vulnerability, is there were some functions in the VMware binary that would allow quick and easy bypass of any DEP-enabled stuff. So it's not really a vulnerability, but it really is the job when trying to exploit that on a Vista host or XP host with DEP, which should be the case with this one. The result of the combination of those three is a reliable guest-to-host escape on recent VMware products. There is Workstation. Fusion has a question mark because the code is here, but I don't have a Mac, so I cannot test or write the exploit. And ESX server, unfortunately, or fortunately for VMware, ESX server is only vulnerable starting at version 4.0, meaning 3.5 and under is safe, as in the feature is not default, but the feature turned to be default in 4.0, meaning that imagine the scenario of having 20, 30 virtual machine running on an ESX server, somebody popping one, getting on the host, and then getting every single other virtual machine from that host. So that was pretty much the point of looking at that. All the bugs in this presentation are fixed. They were fixed in March 2009. It was the disclosure process was pretty weird. They were silently patched, as in they were patched, but there was nothing in the advisory. On March, then we pushed out the exploit in the Canvas early updates program, and then there was like a bit of stuff going on, and then VMware acknowledged the advisory on the 10th of April, saying there was really a guest-to-host escape vulnerability that was patched in the patch 2 weeks ago. Okay, so obviously, since people seem to hopefully follow that, I underline the fact that the video device would be the most interesting device in order to have a look at what was going on. And all the Cloudburst stuff, bugs, are located inside the code that is emulating the video device. The name of the video device is VMware SVGA2. There is a paper that was published recently. We didn't know about the paper at the time we did the research. It's called GPU Virtualization on VMware's Hosted I/O Architecture by Mika Doughty and Jeremy Sugarman. If you want to have some more information about all the technology that is behind that, you probably want to have a look at that paper. As I say in this slide, I'm not a virtualization specialist. I read assembly and try to find bugs in there, meaning that the vocabulary I might be using is probably not the correct one. So if you want to have a more correct view on what's going on, you probably want to read that paper. It has a good insight of all the technology, and especially the 2D, 3D stuff in VMware. VMware SVGA2 is a PCI device that is emulated in the guest. There is no physical instance of that device. It was totally re-implemented by VMware. There is a device driver that is provided to most common guests, understand Windows, Linux, and stuff like that. Only the Windows ones support 3D acceleration, meaning that if you have a Windows guest that is running under Linux or Windows or Mac, then you can play 3D games now, which is a big thing with VMware. Anything that is using extensively DR3 can be played or used under VMware now, which is pretty cool. It's a user-level device simulation process that is responsible for handling accesses to the PCI configuration and I/O space of the SVGA device. Understand it's more like a thread that is running in the VMware VMX process. Here is a bit of more technical stuff that was taken in the presentation of Mika Doty about the VMware stuff. You don't have to worry much about what there is. The only thing that is cool here is that you see that there is some 3 different ways that the PCI device will communicate with the host process. There is the I/O ports, which is you do an assembly in or out in order to send some stuff. There is a frame buffer, which is like if you have in the recent version, it's 128 megabytes of video memory. This memory is split out in 2. There's the 2D frame buffer, which is the pixels that will be displayed. So basically, you write some stuff in the frame buffer, and then it will be displayed as like a 4 byte per pixel, yeah, nothing much. This is shared with some general purpose DMA memory. The DMA memory is usually used in order to put some, if you're using 3D stuff, you'll store some textures and some surfaces in there so that the host can read that and render that. The third and last part, which is the most interesting one, is the FIFO memory. VMware video devices use a FIFO mechanism in order to push command from the guest in the FIFO, and then the host read the FIFO, pulls the commands, and execute that. So there is a bunch of stuff. I will go into the detail of that. Here is the vertical view of that. So you have an application that communicates with the VMware SVGA driver. The VMware SVGA driver is responsible for writing and reading inside the FIFO and the memory region most of the time. And then on the other side, in the host process, there is the emulated device that will read the FIFO, execute command and stuff. The separation is between the guest and the host is located at the FIFO, because the FIFO is shared between the guest and the host, which is represented in the next slide after this one. I will skip that. Basically, memory mapped I/O are complementary methods in order to perform input and output between the CPU and the device. Either you use port or shared memory. If you do, if you use some shared memory or some memory mapped I/O memory, whatever you want to call that, every time the CPU tries to access this memory, then it's caught by the device, and the device performs whichever operation is asked to perform. Here is my simplified version of what's going on in the VMware stuff. You have a guest virtual machine. The guest virtual machine communicates with the virtual video card through I/O ports and I/O memory mappings. Those I/O memory mappings are actually 2 big regions that are located inside the VMware-VMX process. This part is important. If there is something that to remember for the rest of the presentation is this slide. You get that in your head, mostly because everything that will be described afterwards is related, basically getting out of the gray memory region in the host process. Normally, you can only access those gray memory regions, but due to the bugs, you can read out of the gray memory region, meaning that you can access the whole memory space of the VMware VMX process. So keep that in mind. Here is a screenshot of those the I/O ports and the frame buffer and the SVGA FIFO. You get that by right-clicking on your Windows stuff and going into the properties of your video card, and you will see that. So now I've described a bit what was going on with the SVGA device, and I will go into the detail of the FIFO and how it works and exactly what's happening with VMware. So the SVGA device processes commands asynchronously via lockless FIFO queue. This is from the document. Again, I'm quoting the document. This queue is several megabytes wide and occupies the memory mapping that is marked in the previous slide as the FIFO memory region. There is two different ways, there's two different types of commands that will be processed by the host OS, or that will be sent from the guest to the host and processed by the host. Those are 2D commands and 3D commands. The 2D commands are pretty much like regular stuff that happens on the screen. Basically, if there is something that has changed in the frame buffer, like you've updated some pixels, then you send a command that will say, please update this rectangle on the screen that is 100 pixel wide and 100 pixel of height. And you send that, and then the host receives that, and then updates the screen on the host side. There are some a bit more complex commands that are related to drawing cursors or storing cursors or displaying glyphs or some other stuff, but usually it's pretty simple commands like update the whole, refresh the whole screen, copy a rectangle from point A to point B and stuff like that. On the other side, the 3D commands are a lot more complex. I will go into the detail, but basically it's the FIFO is used as a transport layer for an architecture-independent 3D rendering protocol that VMware developed. They abstracted DirectX3D in order to make their own stuff, and basically from the guest, the driver will send something to the host saying, here is I want to execute this 3D command with these parameters, and you have to do that. So it's some kind of like rewrote DirectX3D stuff or transport layer for DirectX3D in order to be able to have 3D acceleration inside the guest. Here are some 2D FIFO operations. The cool thing about those is you can find the code in the VMware XF886 drivers because it's open source. You can read that. There's a bunch of 2D commands in there. Everything is defined. There is the names, there is the parameters and everything, which is not the case for 3D. But it helps a lot if you're trying to figure out how this FIFO stuff works, how the guest driver is sending command, and how the commands are interpreted by the guest. The command number 1, for example, is called SVGA CMD update. It takes an X, a Y, a width, and a height, and then it updates a rectangle on the screen. Pretty straightforward. The second one is called SVGA CMD rect fill. This one takes an additional parameter that is the color, and then it will fill up a rectangle with a given color. So once again, very simple command, not too many parameters. Third one is called SVGA CMD rect copy. That takes an X and a Y, a source XY, a destination XY, a width and a height, and it will copy the rectangle, the source rectangle, to the destination rectangle. You might already know where this is going. Here is a list of all the SVGA 2D operations. I've colored that because it has changed a lot since the beginning of VMware, but most of them were present since the very first versions of VMware. The one in green are default and accessible by default under VMware. The one in yellow at the bottom right of the slide are not default, but can be turned on from the guest by a special command, so they can be considered default. The black ones are not default and require an option to be turned on in the VMX configuration file for the virtual machine. And the ones that are stricken are commands that have been deprecated and are no longer in use. Usually they just return without doing anything. So auditing this part, you pretty much want to focus on the green and yellow and try to find something in there. I would have thought that this was a lost cause at the beginning because every single command only takes like 4 parameters and they're really simple. It turns out it was not. Here is the representation of the CMD rect copy operation. I've represented the frame buffer by a big screen in order to like be less abstract. So you specify a source rectangle in this frame buffer and you specify the destination. It will just get all the pixels in this rectangle, copy that in the destination rectangle, and you will see the update on your screen. The stuff here, the stuff that you have to remember is the screen that is displayed is actually one of the 2 grade memory area in the host process. It's the frame buffer memory area. Meaning that some weird stuff can happen here. Here is the first bug of rect copy. There is some boundaries check on the source rectangle. If you specify an X and a Y that are like outside of the screen, you would think that you should not be able to do that. Fortunately, the checks were signed, and you could pass like through some tricks. You could get some negative X and negative Y, meaning that you're reading memory as the source rectangle that is outside of the visual screen. What does it mean? It means that you have your gray memory region. Normally, you could only read and write in this memory region. Using this command, it means that you're reading outside of the gray memory region and you're writing the result of the read operation inside the gray memory region. Once again, the gray memory region is shared between the host and the guest, meaning the guest has access to the gray memory region. It should not have access to anything outside. So this third bug, what does it mean? It means that if you specify negative X and Y, you can read any part of the host process memory, or at least the part that are before the frame buffer, which is pretty much like everything you need to, and read that memory and write that in the gray memory region. Then from the guest, you just have to read the pixels, and well, it means that you can pretty much read any part of the host memory from the guest without too much trouble. So that's the first vulnerability that was in the 2D code. Remember, the rect copy operation only took 6 parameters, and it was like only X, Y, width, height, and it turns out to be vulnerable. As an addition, this vulnerability has been there since pretty much the very beginning of VMware, and you could do that because it's like a very basic, one of the first 2D commands that was added to VMware. It was only found in 2009, at least publicly. The rect copy operation, obviously, you're thinking, or you should be thinking, if I can have a negative source abscess and a negative source X and Y, then I could probably do that with the destination. And this is correct. Unfortunately, the checks are a bit tighter on the destination rectangle, meaning that you can have, you can send the command. What you can do is fill your frame buffer with pixels, those pixels being not real pixels, but actually data you want to write in the host memory. So you put that in the gray memory region, you invoke the command, the CMD rect copy operation, and those fake pixels will be copied outside of the gray memory region, and they will be put inside the host process memory. Which is pretty cool. It means that you can, that's an arbitrary write. It's a relative write because the negative X and Y are relative to the first pixel of the frame buffer, meaning that you will write 10 bytes before the frame buffer, 100 bytes before the frame buffer, but if you don't know where your frame buffer is, then you cannot really like have a reliable write. Which is why the previous one is pretty useful, because with the memory leak from the host into the guest, you can have the address of the frame buffer inside the host memory region, and then you can use the right primitive in order to get that. The problem is that you can only write in the few pages before the frame buffer, and unfortunately in our test there was nothing really interesting in those pages. The checks were not allowing you to write wherever you wanted, only those first pages right before the frame buffer, and it turns out to not be useful for exploiting or fully exploiting VMware. Here's a summary of the previous slide. Once again, a guest can read and write into the frame buffer. It's your pixels. It's what you want to display on your screen, so obviously you can have access to that. The frame buffer is mapped in the host memory, meaning that the CMD rect copy bugs mean that one can have a default unlimited arbitrary read of anything that is in the host process, and obviously recover the data by reading the pixels. And the second one means that you have a default, unfortunately limited arbitrary write. You can write whatever you want only in the first pages before the frame buffer. So at this point, it's only like pretty much the beginning of the audit, but it turns out that it's going to be fun. And we'll go on with some other bugs and how to like click them all together. Here's another cool command that is unfortunately not default. It's the CMD drawglyph. Drawglyph take as parameter a x, a y, and then a bunch of pixels, and it will like just put those pixels whenever it was told to put them. It requires a command in the VMX configuration file for the workstation that is svga.esglyph equal true. So it's not, unfortunately, not default, but as you can probably guess, there is absolutely no check on the X and the Y, meaning that you're giving out a bunch of pixels and you say write those pixels at X and Y. If you're specifying your X and Y to be -100 or -200 for stuff, then you're writing this bunch of pixels in the host memory area. This means that you have a non-default unlimited arbitrary write. Once again, it's a relative write because it's -X and -1 compared to the first pixel of the frame buffer. You still have to know the address of that first pixel in the host memory in order to have something that would be a lot better to exploit. So at this point, we have pretty much, unfortunately, like a memory leak. We can leak anything from the host into the guest, but we cannot really write by default anything anywhere from the guest into the host. So we have to continue searching and hopefully try to find something else. This is when, well, we pretty much went through all the 2D commands and turns out there was nothing that would allow a default write. So we turned to 3D. 3D was introduced recently in the VMware product. The first 3D commands appeared in VMware Workstation 5.0 in April 2005, according to the documentation again. They were disabled by default. At the time, you have to add something in the .vmx in order to get there. The cool thing is that they became default with Workstation 6.5, and whichever version of Fusion is shares the code with 6.5. There is a checkbox now. There is ASLR 3D graphics under the configuration option of the VM. And if you check that box, then the VM will advertise that it can do 3D. So you can install Direct3D and run some 3D stuff. The cool thing, or the annoying thing for VMware, is that even if you uncheck the checkbox, the code will be executed. Meaning if you're sending through the FIFO or 3D command, then it will be executed and will pop an error message saying, sorry, I cannot execute that. But the error message is popped after the execution of the command. Meaning that even if you do not enable 3D, then you're still vulnerable. Which is cool for ESX4, because ESX4 has the exact same stuff. You would think that there is no need for a virtual machine in an ESX to have 3D, because you only connect either through the console, which is VNC, or through terminal server, stuff like that, meaning there shouldn't really be a need for 3D there. The cool thing is that the code is always shared between all the versions of VMware, and you get 3D operations enabled in ESX4 release candidate by default. So you can also exploit all the 3D commands that will be described. Obviously, the 2D commands are enabled on all the machines, meaning that the memory leak also happens on ESX. But on this one, it turns out to be pretty useful. Unfortunately, the bug died before ESX4 final, so we only did the proof of concept on ESX4 release candidate. A few words about SVJ 3D. It's a simplified and idealized adaptation of the Direct3D API, according to VMware. It has a minimal number of distinct commands. There is no public documentation about it, as far as I know. If you look at the current XF86 drivers, there is some definitions for some 3D constants, but there is actually no 3D commands and no code at all for 3D stuff. The thing that will be useful for the rest of the presentation is that it uses contexts like Direct3D. A context is a big structure that will be allocated in the host, and this structure will hold all of the 3D relevant variables that you can set. Through Direct3D calls, such as render states, light data, etc. I'm not a 3D specialist, so that doesn't mean anything to me except names or symbols in the binaries. Here's a list of all the 3D operations. There's a bunch of them. As you can see, there is some define commands, some set commands, and stuff like that. The way it works is exactly like 2D. You send through the FIFO, you send the command you want to invoke, then a list of the parameters. The cool thing is that every single 3D command is enabled. There is no such thing as non-default 3D command, meaning that if you have 3D, you have access to all of them. Starting from there, you can, I had a look at all the 3D commands one by one in order to see what they were doing without previous knowledge of Direct3D, so it was pretty painful. The cool stuff is that there is a bunch of set commands. Set will take whichever you like, the variable you want to set and the value. There is like, for example, this command set render state. Most of the set commands appear to be flowed, which turns out to be pretty interesting. What happens is, through the FIFO, from the guest, you send a command saying, I want to invoke the command set render state, and I want to set this state to this value. The state is an index in an array. And as you can see here, it will read the index, then the value, then write the value at the index inside the context, but there's absolutely no bound checking on the index, meaning that usually index will be something, or the render states will be something between 0 and maybe 32 or something like that. But you can pass -16 if you want, you can pass 1024, and you will like write some memory outside of the context and do some stuff. So this set render state command gives you an arbitrary write, but once again, it's relative write. If you look at the code, you're writing something at ESI plus EDI times 4 plus 50, meaning that if you don't know ESI, then you don't really know where you're writing your stuff. You're writing something before ESI, after ESI, you don't really know where ESI is, which is where the memory leak comes useful, because you can leak the address of the context that was allocated thanks to the 2D rect copy bug, and then your relative memory write turns out to be pretty reliable. There is another another trick that can be used. This is the set light enable code. The light enabled code reads a pointer in the context and writes something at this pointer. The cool thing is that since we have a relative memory write, inside the context, we can basically override this pointer, then invoke the set light enabled command, and then from the relative write primitive, meaning write something relative to the beginning of the context, we get something that is an absolute memory write, meaning that we've overwritten the pointer and then something is written at this pointer. So the pointer is located at context plus 648 if you want to have a look at that. There is many more bugs, like pretty much all the 3 comments were pretty bad. Set render target has a signed bounds checking, meaning that you can pass negative parameters to that. Set clip plane has no bounds checking. Set transform has no bounds checking either. So all those comments allow you to have some like write operation from the guest into the host memory. So you've seen at this stage we have a bunch of vulnerabilities that would allow some memory leak from the guest to leak some memory of the host inside the guest, and some arbitrary memory write from the guest into the host. So now we just have to get all of this, put this all together in order to write something that would be a reliable exploit at some point, which will happen. Okay, here are a few requirements for exploiting those vulnerabilities. We have to be able to read and to write directly into the frame buffer and the FIFO. We have to read and write directly into the frame buffer, obviously, because if we want to recover the result of a memory leak, we have to read the pixels on the screen in order to get those results. If we want to have to exploit an arbitrary memory write, we have to put whichever pixels we want into the frame buffer, and then this will be sent to the host. So there is some Direct3D APIs in order to have access directly to the frame buffer, not the FIFO, unfortunately. But most of them are checked and sanitized and turns out not to be extremely cool. So the solution was to write our own driver inside the guest in order to be able to access directly the memory pages without having to care about anything else that would slow us down. It can, the one we did sits on top of the VMware video drivers. It's easier this way because you have less to code, but you don't need that, meaning you don't have to have VMware tools installed in the guest in order to exploit that. You just have to write a lot more code and a lot more video driver code, which turns out to be extremely painful. And this way we can map the FIFO from inside the guest, you map the FIFO. Those are just memory regions that are accessible in ring 0. So you map the FIFO, you map the frame buffer, and you can do whatever you want. So the real requirement is to have admin rights inside the guest, which is most of the time not too complex, either using some local privilege escalation or compromising somebody who is already admin rights, or getting in the VM, for example, using a worm or any wormable exploit, think honeypots and stuff like that. They get on all day in order to recover some data. So just get there, you have admin rights, you run the driver, and then you're good. Here is a few steps for the exploitation process under that was our first attempt on Vista. The first step, which is no longer required after the turning relative write into absolute write, was to leak the base address of the frame buffer inside the host memory. Once again, every single relative stuff, relative leak we're going to do is based on the address of the pixel 00, because we're reading -50 from that pixel, -100 from that pixel. So we have to have this address. It's pretty easy to do that under Vista, because right before the frame buffer, in the host memory, there is the address of the frame buffer. So you just have to leak the 16 bytes before the frame buffer to get there, and it was pretty fast. Under Ubuntu, we did a relative leak brute force. You just you pretty much know where you are. Most of the time there is a bit of randomization or a bit like of changes in the frame buffer base address. So you try to leak the content of the VMware binary, which is most of the time at a given distance. So you leak, you change the address until you reach the PE header or the ELF header, sorry. And once you reach the ELF header, you know the distance between the beginning of the header, which is always mapped at the same spot, and the base address of the frame buffer. So that was the second stuff we used to exploit that on Ubuntu. It turns out to be a bit slower, but almost as reliable. Under XP and Vista, we tried another thing that is an absolute memory write using the trick with the set light enable. So you do an absolute memory write at this address. It turns out that since the frame buffer is 128 megabytes, it takes a huge portion of the host process memory. And it's always pretty much mapped at the same address or between the same addresses, except on the EEPC, obviously, which is where I'm doing the demo, which turns out to have changed a lot. But other than that, you just like write something in your frame buffer, and then you write something at a given memory address, then you scan your frame buffer, and then by subtracting the position relatively to the beginning of the frame buffer, then you have the absolute memory location of the frame buffer in the host. Then once you have the address of the frame buffer in the host memory, you basically cycle between leaking and writing, leaking, writing, leaking, writing. The first step of the leak is usually to leak the PE header or the ELF header in order to know where you're, what the version of VMware Workstation or whatever you're in. And then once you have that, you have a bunch of addresses that you have coded into your exploit, and you can leak overwrite trigger, and stuff like that. And we'll see exactly how it looks like. Here's a screenshot of what the leak looks like. As I told you, when you're triggering a leak, you're getting some data from the host into the frame buffer, which is visualized by the screen you're seeing here. The way we do that is always using the first line of the frame buffer. So when you're magnifying the first line of the frame buffer here in the VM, which is at the bottom, you see a bunch of weird pixels that are located here. Those weird pixels are actually the content of the host memory that was leaked into the guest. Since in the guest you can read all the pixels of the screen because it's your screen, that's your stuff, you can read that and then recover the information you needed. When dealing with DEP, there was like something that was extremely interesting, and that is the fourth vulnerability, but that is not really a vulnerability, that's more a functionality. When you want to exploit that on ESX4 or XP and Vista with DEP enabled, you have to care about NX and the fact that you cannot write and execute anything you want anywhere you want. In order to help us, apparently VMware-VMX provides some virtual protect wrappers, and those wrappers actually take their parameters from the data section of the binary. This is extremely useful because it means that most of the time when you have to disable DEP and stuff like that, you have to forge your stack and do some stuff. Here, it means that you just have to override two parameters in the data section. Data section is always at the same location. You can do that with your absolute memory write once you've fingerprinted your VMware version. And then you call the wrapper by overwriting a function pointer and calling the function pointer. And then it will just switch the protection to read write or read execute. Turns out to help us a lot when exploiting that because you don't have to forge your stack frame and everything. You just have to exploit that this way. I will. Well, there is 12 steps in the first exploitation attempt that we did on Vista, I think it was. I will like fly through that, but it's pretty much to make you understand that nowadays, as pretty much was, well, like all the presentations nowadays tend to point out, it takes a lot more than a single stack overflow and then overwriting EIP in order to get a reliable exploit and to get something that would work. So yeah, it takes 12 steps there in order to go through like executing something into the guest to executing something into the host. First step is leaking the frame buffer address into the guest, then leaking the PE header in order to have the version of the VMware binary. Then we leak some more structures. Those structures are needed in order to get the address of the context, the 3D context, and do some stuff. Leaking the 3D context is not really longer useful anymore thanks to the relative to absolute right stuff. Then you overwrite the virtual protect wrapper parameters in the data section. Then you overwrite a function pointer. We used a 2D command, function pointer that is triggered by a 2D command because we're still sticking into the SVGA device. So we call the virtual protect wrapper. At this point, we have something that is read and writable. Then we write the whole shell code into this memory area. Then we overwrite once again the virtual protect wrappers parameters to something to this memory area. Then we switch the page back to read and execute. Then we overwrite another function pointer with something that is pointing to that, and then we execute that function pointer thanks to the 2D command. Then we have something that works on Vista SP1. Obviously defeats ASLR and NX by the fact that we're linking all the address we want and the fact that the VMware binary is always mapped at the same address, and that's pretty much it for Vista. So at this point, we have an exploit, but then once you have that and once you have execution on the host from the guest, you have to ensure to have a communication channel between the host and the guest and you pretty much. Most of the time you will just say, or you will just assume that there is networking on the host or there is something else. We preferred to assume there was nothing there, and we didn't want to rely on any of the functionalities that could be disabled by the administrator and stuff like that. So what we came up with was MOSDEF over Direct3D, which is you tunnel your shell, the shell you got on the host, over BMP, over the frame buffer, which is pretty interesting. So MOSDEF is something that Dave came up with. It's, according to his definition that I don't really understand, it's a retargetable position-independent code C compiler that supports dynamic remote code linking, and it's written in Python. Basically, once you've overflowed the process, you can compile whatever you want inside that process, and it will report back to you. So what we wanted to have is to ensure host to us communication or host to guest without relying on stuff that can be disabled. We assumed there was no networking between the guest and the host, meaning you can just not have a bind shell on the host and then do that. We assumed there was no VMCI because it's disabled by default, and we didn't want to deal with VMRPC because it can be disabled in the configuration stuff. The idea was to tunnel the shell over the frame buffer because we like the fact that once you're like touching something that is in one component, you will not use anything that is in another component of the stuff. So we stick with the SVGA device and we stick with the frame buffer and do everything. And what we wanted to do is do that in ring 3 in order to add a bit of spice because well, you cannot access you can access obviously the frame buffer and do that in ring 0. But after that, if you want to have a layer of TCP/IP communication in ring 0, it's pretty painful. While it's pretty easy to have that in ring 3, so we decided to try and have access to the frame buffer in ring 3. As I told earlier in one of the previous slides, you can do that with Direct3D APIs. So we'll go over exactly what we do. On the guest side, we will create and manipulate objects, surfaces, in the video card memory off-screen. Off-screen means you have 128 megabytes for your frame buffer. You have your pixels, and after those pixels, you have a bunch of memory that I told you was used for surfaces and textures and stuff like that. So what we're going to do is use the Direct3D APIs in order to write fake surfaces in there, and those fake surfaces will actually be something that will be grabbed on the host side, interpreted, and then written back and then executed. So there is create off-screen plain surface. The only thing, if you want to play with that, you only have to care about the fact that you want 32 bits per pixel. Otherwise, that will be painful. And then there is a D3, DX load surface from memory. So you just give a bunch of bytes, and Direct3D will load those bytes off screen into the frame buffer. And then there is save surface to file in memory. The problem is that there is no save surface to memory directly. You can only save that as a file. So, and there is no raw format, so you have to save that as a BMP, which is why when you're grabbing back the stuff from the frame buffer into the guest in order to send that back to you, you have to parse the BMP that will that is actually a fake BMP, but that will actually have the answer to your request in there. On the host side, once we've exploited the bug, on the host side we run a shellcode. The shellcode will run a MOSDEF listener on localhost and then thread out another thread. This thread's job will be to scan the frame buffer in the host memory, find a signature. Once the signature is found, extract the data, send that to the locally bound MOSDEF, receive the data, then put that back into the frame buffer, and then on the guest side will get the surface again and parse the data like that. So this way we tunnel our shell over the frame buffer, and since MOSDEF is acting sequentially, there is no concurrency issue most of the time, but we just have like a loosey semaphore scheme in order to be sure that there is no reading and writing of the same surface at the same time from both the guest and the host, which shouldn't happen. So the result that we have for that is that's a diagram that is taken from the HP NetTop stuff, where they have over SE Linux 2 virtual machines. One is doing classified, the other one is doing unclassified, and they're supposed to be totally separated. There is nothing that should be doing anything between the guest and the host. There is nothing that could communicate to the two virtual machines. So by building this thing, by imagine going through internet, exploiting the unclassified machine, then you get pretty much a shell on the host, and then you can build also some type of bridge between the classified version of that and the unclassified version. We didn't do that because we don't have a HP NetTop, but we did that with some Vista SP1 stuff, which is not as good as SE Linux, but it's pretty good now. So there will be a demonstration, hopefully after the conclusion. A few misconceptions about virtualization is that most of the people would think it can be taken as a security layer, as something. If you run something in a VM, then you're safe. This is totally not the case. It acts probably as an additional barrier that an attacker has to jump over in order to get there, but it's not impossible. And as hopefully proven with those slides, there's a bunch of stuff that can be done between the guests in order to get into the host and stuff. Once again, we only did the first device that was in the list, and everything is about that first device. Given the correct bug primitive, you can defeat everything. If you have a memory leak and a memory write, like we have, you can defeat ASLR. There is no need to randomize any of the memory because you can leak it and then recover the pointer and then you're done. You can defeat NX, obviously. That was, the VMware Virtual Protect wrapper helped a lot for that. But yeah, you can do fancy stuff. One of the stuff also that is if you're trying to patch something silently in 2009, It's not going to happen. There's always people patching binary thanks to Alvar's tools and others. But if you're like trying to hide something in a patch, that's not going to happen really. And one thing also that is pretty weird, and I don't really know what it happened, is that if a feature is not needed for a branch of your product, I would think here about the 3D stuff for ESX, there is no need for the code to be included in the release, and there is no need for the code to be executed if somebody has unchecked the checkbox that says, I don't want 3D support. So now I will try and demo that. So there is like a bit of warning here, is having a VMware XP under EPC is probably not the best idea I've had because it's extremely slow and not extremely reliable. So it works usually, but we'll see. So the way I'm demonstrating that is that I'm going to use Canvas in order to first exploit MSO8 067, like we have an XP on the other box. Let's see if I can show that there. So we have a vulnerable XP on this box here. I'm going to get into this virtual machine by exploiting MSO8 067. Okay, you have to see that really. Okay, it takes a bit of time because the like I have a crappy hub and everything. So the first step, well, the stuff Canvas is doing is fingerprinting the other machine, then detecting its XPSV2 English, then getting the target, the correct target for MSO8 067. Then now it's getting the node. So that's what it looks like now. I'm not sure it's really visible, but the IP of the attacker is 10.10.1. The IP of the virtual guest stuff is 10.10.3. The IP of the host is 10.10.2. So at this stage, I have a shell. Obviously, I'm an administrator because that's MSO8 067. It's running a system. So I should be able, I'm selecting the node by clicking on it. So you see it like changes color, it's fun. And then you click on, well, the Cloudburst stuff. So that's where it can do fancy stuff or crash my VM or stuff like that, we'll see. What it does is it will upload the sys, the .sys, the driver, and as well as the MOSDEF or Direct3D thingy. And then if everything goes correctly and the stuff is not crashing, there will be a second node that will appear, and this node will have the IP 10.10.2, meaning the host, and then I will like try and take a screenshot of it. So here it appears to be working because we got the second connect back, which is the lines that are like appearing at the bottom of the screen. Okay, so we got the second node here. Here, the IP of the second node is 10.10.2, meaning that we have currently a shell on the host. What happens is that, as you see, there is a red link between 10.10.1 and 10.10.2. It's actually not correct, but because it should be a red link, well, there is no abstraction layer for that, but everything is tunneled through the frame buffer to 10.10.3, and the packets are actually coming from 10.10.3 to 10.10.1. Now, if I'm selecting this node and going into the commands, I'm going to do a screen grab. Yeah. Screen grab. So it will take a bit of time. Everything that we're doing now, we're sending a shellcode whose aim is to take a screenshot. The shellcode is sent to 10.10.3, tunneled over the frame buffer to 10.10.2, executed. Then the screenshot itself is tunneled back over BMP through the frame buffer to 10.10.3, and the packets are coming back from 10.10.3 to 10.10.1, which turns out to be like a lot of going back and forth stuff. And now we should have a screenshot, except I don't see exactly where I'm clicking. Okay, here's the list for screenshot stuff. And here is the screenshot of the host this time. Okay, here's the screenshot. So on the host here, what I wanted to point out, I have Process Explorer. You can see VMware is running. There is Immunity Debugger for like advertising purpose here on the taskbar. What I wanted to show is that the VMware-VMX process is running with DEP enabled. So this is the one cool scenario case, and it's even working on the EPC. So it's awesome. That's it for the presentation. If you have any questions, feel free to come and talk to me after the presentation.